My name's Steve Fitzpatrick. I'm trained as a geologist, specifically a hydrogeologist, but through the course of my studies, I had to do, when somebody's in hydrogeology or geology or hydrology, you deal with a lot of forestry issues. You deal with a lot of soil and water issues, of course. And I ended up taking some classes at the Warnell School of Forestry, and through that, and the fact that my advisor, Dr. John Dowd, was a fire jumper as his first career before he became a professor. He got me interested in fire weather, specifically wildfires, and I ended up doing a presentation for a graduate level geography class that I took on GIS, global, graphing in GIS. Okay. So I did this presentation, and I did it on modeling wildfires with the use of GIS technology. This talk, I made it a little more broad-based to cover science in general, because the GIS-fueled talk about wildfire and wildfire modeling is just a little too specific. But we're going to touch on modeling too, because of course modeling's very important in science. You have to use it. Okay. Now, wildfires, or wildland fires as they used to be known, are defined as any uncontrolled burning of vegetation in the countryside or wilderness. Now, wildfires are set apart from any other kind of fire by their extensive size or increased speed or rate of spread, which is fueled by wind to a large part. You get a 30-mile-per-hour wind, you can have a fire that goes 30 miles an hour. You can have a fire that goes up a hill faster than across level land. They're very dangerous that way, and it's part of it's because there are updrafts. Hot air rises, and it fuels the fire. It causes the fire to spread upwards. There's a potential for sudden change in direction with wind direction. The ability to jump gaps such as roads, rivers, and fire breaks. And this can happen because there's enormous heat. And this enormous heat can cause these columns of hot air to send out fuel materials, which can spark on the other side, especially during a drought. Now, wildfires are also characterized in terms of the cause of ignition. Their physical properties such as speed of propagation, the combustible material present, and the effect of weather on fire. The fuel is very important, especially when you're modeling wildfires. The fuel is often your underbrush, which becomes dried and desiccated. Once it dies, you gather up enough underbrush, you get enough dry conditions, and you just light it with maybe a lightning strike, and you have a wildfire. Okay. Fire occurs due to combustion or it's a rapid exothermic oxidation reduction reaction. That's exactly what fire is. It's just very rapid. Fire itself is gas. It's a superheated gas. Okay? Superheated gas that emits heat as well as light. Fire begins with fuels that are subject to the right amount of heat and the correct amount of dehydration. Dehydration is extremely important because this is where you get a lot of your forest fires down in South Georgia. In the drought period back in 2007, huge fires down near Waycross. That's because of dry conditions. The water is just not in the air, and the water helps to attenuate any chance of combustion. The converted products of combustion are often as combustible as the fuels, since these materials are converted to char. Now, char is your black woody material that's left behind. It's that black stuff you see in a campfire. It's very combustible. It's almost pure carbon. The speed of the fire front is often dependent on wind velocity, and all of these conditions creates a field of study known as fire weather. I'd mentioned my advisor. He actually studied under a gentleman who I believe worked out west, and his specialty was fire weather. So fire weather is a field. Wildfires require dry conditions. The greater amount of water present, the less likely for a fire to begin. Fire requires heat to begin and a continuous application of the correct amount of heat to continue. The heat creates dry conditions. It's a constant positive feedback. At a fire front, as it's advancing, a really, really raging wildfire out in the wilderness is going to have up to 1,000 degrees Fahrenheit in front of it of heat actually convecting, possibly convecting off of it. in the air, this heat will instantly dehydrate anything. All that instantly dehydrated material that fuel needs is just a little spark, and it comes up. So you actually have a sort of advanced warning system for fire there that's naturally built in. Fire requires fuel. Fire is a chemical reaction. Without this fuel, fire cannot continue. You run out of fuel. Fire gets to, let's say you're in Arizona, or maybe Nevada's a better example. Actually, Utah is a better example. Okay, fire gets right up to rock, can't go any further. It's just about that simple. Fire requires oxygen. It's an oxidizing reaction. The wildfire front, the moving line of combustion, is a forest fire. In a forest fire, acts to sustain a wildfire. Like I mentioned, those temperatures, 800 degrees centigrade, get enormously hot. Air rises as it heats, and this creates strong thermal updrafts, which can lead to fire, what they call fire stacking. And this is where you get fires that literally go straight up. And these updrafts will go to the top, to the canopy of some of these pine forests, and a tree will just go up like a match. Okay, it also goes uphill. Like I mentioned, these things can go 30 miles an hour uphill. You can't outrun them. Okay, what are the causes of wildfires? Well, wildfires originate through human activities and natural processes. Wildfires are a natural process. They need to happen. We'll go over that in a minute. But here's a sort of a graph. I think this was done in the Northwest. So each region has its own different, set of needs. But this is pretty much how it occurs. Most of your campfires, your wildfires are going to be arson. There's a large portion of these are arson, believe it or not. I don't know who's setting these fires, but arson always is a big slice of the pie. Children, okay. Railroads, I don't know how that happens, but railroads. Debris burns. People are burning in their backyard. A spark gets off. This is probably it's probably very, very relevant to California. Okay, because California has a big problem with wildfires because it has these dry woods, that Mediterranean climate, that go right up to houses. Okay, and then, smoking, people throwing their butts out, campfires, and lightning. Lightning, surprisingly, takes just a small part of the pie, but lightning strikes are the most common natural occurrence for wildfires. And this is where wildfires are actually necessary.
This is when somebody's burning like a building for insurance purposes.
Yeah.
But they're not trying to burn the forest.
I don't know. You know what I'm thinking?
I think I read in California where they're trying to burn the forest.
Yeah. Yeah, you can own land, and maybe you're going to get some insurance off that land, So.
Or just plain mischief.
Yeah.
Which is every bit as devastating.
Yeah, exactly. Okay, and forested ecosystems need fire. Wildfires are necessary, they're natural processes, and fire reduces the overaccumulation of plant growth, specifically undergrowth. It's that undergrowth, if you accumulate a lot of it, and you have dried conditions, you just have tinder, and it'll go up. Okay. Also, this underbrush inhibits the growth of other species. You get rid of it, and you can allow other species to proliferate. Forests naturally burn. They have to. Okay. Fire can stimulate growth and the reproduction of some plants and require it, and it also makes room for habitats. For example, there's a tree out west called the lodgepole pine, and the only way that it dislodges its seeds from its pine cones is by being heated. And forest fires heat these pine cones, and the pine cones drop their seeds. This is how the lodgepole pine proliferates. So, there's also something that the Forest Service does called using prescribed fires. Okay, and this is where they purposefully set the forest on fire. Major reason for this is that when undergrowth proliferates, dies, it becomes dry and becomes a fuel. Also, we've gotten so good at, believe it or not, we've gotten so good at preventing a lot of forest fires, we actually allow for this underbrush to proliferate where it naturally wouldn't, okay, because we're preventing a lot of fires. Well, this underbrush is what causes a lot of these is a fuel and causes, a sort of an exacerbation of the process. An overaccumulation of the fuel increases the chance of out-of-control wildfires. Another reason to set controlled fires is to prepare, there's several other reasons. One of the reasons is to prepare sites for seeding and planting. You want to clear the land to plant. Forestry does this, I believe. Dispose of logging debris, which is actually very relevant to Georgia because timber is one of our biggest, if not the biggest industry in Georgia. Improve wildlife habitat, manage competing vegetation, control diseases, and it's a good way to help recycle nutrients or cycle nutrients through. The U.S. Forest Service actually has a pamphlet which they use called A Guide for a Prescribed Fire in Southern Forests, and I used it as citation, and that's what that person's doing there, setting a fire. In 1910, Congress appropriated funds to aid in wildland fire suppression by the National Forest Service. This sort of started the whole cycle there. And we were talking about controlled fires. Also, the U.S. Forest Service spent $1.4 billion for fire suppression in 2007, and some of that was Waycross. Some of that was what was going on in South Georgia. Urban areas continue to encroach on wildlands, and we're seeing wildfires affecting people in their homes. We're seeing businesses now being affected on a larger scale because, development is encroaching on wilderness lands. This is happening in North Georgia right now. Okay, and here's a map, a choropleth map of, and a choropleth map is a map that shows statistical data over a predefined area. That's the definition of a choropleth map. It's sort of got the aerial distribution of reported wildfires for that month in 2009. And you take this and you can sort of think forward to the next month and know, okay, we have a danger here. Once again, oddly enough, South Georgia, you don't think of it as a big wildfire. Of course it's not. You get a lot of these fires in these regions. The West has a particular problem with it. Montana, there's been some incredible forest fires there. The Man Gulch fire, we'll go over that in a minute, back in 1949. Each area of the fire danger is denoted from low to extreme. High is part of Georgia, so there's generally a high danger level depending on the amount of moisture in the air, depending on the precipitation that's occurring at the time in South Georgia. Okay, and then the long-standing wildfires back in the summer of 2007. I remember them going on for a few weeks. I was in Colorado at the time, but I was paying attention to the news, and they were there for a couple of weeks. Okay, well, to understand fire, you have to do fire research, and this has been going on for quite some time, backed by the U.S. Forest Service. Okay, the costs of unchecked wildfires would be considerably higher, especially in terms of environmental costs, were it not for prevention techniques. One of the pioneers was Harry T. Gisborne. That's him right there. And he developed a simple model known as the fire danger meter, which continues to be used today. He developed it in 1931. In 1949, there was that fire that I mentioned near Helena, Montana, called the Man Gulch fire. It was an enormous fire, very devastating. Well, Gisborne decided he wanted to research this fire to a T, and he spent all of his time out there putting forth basically a Herculean effort, and it killed him. He died from the efforts, possibly from smoke inhalation too, of his research into this fire. And the data he collected like a mountain of data, and it continues to be used today. We use it today. The people that developed models back in the 70s, like Rothermel, we're about to talk about Richard Rothermel, used his data because it was so precise and it was so huge and it was so detailed. And it killed the guy. The data he collected helped decades-long intensive research. Ultimately, Richard Rothermel and his team in 1971 and 72 developed the Rothermel model, and it's a very robust tool. After Rothermel, a researcher who's a very astute mathematician named Frank Albini took it further and created another tool, a series of graphs called nomograms.
This is a model of how fire burns or how the danger?
How it propagates, how it burns across an area, where it's going to be, where you think it might be.
Oh, so it's also prediction
Yeah,
hazard.
yeah. So you know, you model it and you go, okay, that fire has a great chance of crossing that, divide there. So and this is where the fire, the people that fight fire, they get out there and they'll put their lines down and, try to prevent the fire. This is his his fire danger meter. See, it's just really simple. It's just a sort of a little dial-up graph there. It's a simple model for fire estimation. It's a slide rule-like device. It takes into account parameters and variables such as fuel moisture, condition of vegetation, wind velocity, a few other parameters. There have been a lot of modifications. People are still using these, and they're making new ones. So there's been a lot of variations, there's been a lot of work done on these. In fact, you can buy them online. The fire danger meter is a type of model. Okay, models are really important in science because, especially the natural sciences, because like biology, geology, astronomy, forest science, soil science, all that, because they allow you to understand processes before and after the occurrence, and they also allow you to make predictions. Something like this, forest fire prevention, you want to make accurate predictions. And that's Richard Rothermel. In 1972, Richard C. Rothermel is a research engineer for the USDA, introduced a mathematical model that was applicable to the prediction of both fire spread and intensity in forests, brush fire, and grasslands. So yeah, it's mostly a fire spread model. The model is used today, and it's been upgraded. Very mathematically astute people like Frank Albini have done further derivations on it. Taken some of the functions that Rothermel came up with and done further derivation and things like that. But a lot of the models employ remote sensing, and a lot of the models, rather than do an analytical solution means you're using calculus. A lot of these, for ease of use, use a finite difference or finite element type background, which is more of what they call a numerical model. And a finite difference, you take the difference of the first and you get to the next. Finite element is actually a lattice work, it's a grid, and it uses matrix equations. So they can get pretty complicated. Okay. Also, using something called cellular automata, which actually is related to finite element, and there's even neural networks that they're developing to sort of model the way these things behave. Richard Rothermel's mathematical models for the prevention of fire spread assumes very few parameters. And the parameters of importance involve the characterization of the fuel itself. He was very focused on the fuel, what the properties of the fuel were. Apparently this worked. Apparently for the conditions he was dealing with up in the Northwest, this worked. So within Richard Rothermel's model, the physical and chemical characteristics of the fuel are key. So you're dealing with the fuel a lot. The concept is that of a fuel model wherein parameters of wild fuels are necessary for input to the model are characterized and tabulated. So it's a fuel-based model. Okay. Inputs are used to predict fire spread and intensity, and it is founded on the concept that fuels have inherent characteristics that are predictable. You can take your fuel, whatever type of underbrush it is, and depending on the application of heat, dehydration, and whatnot, you will get a fire. Well, there's one page of his. This was another page. It's from the actual pamphlet, which I found online. The main equations of the model relate to the rate of fire spread, feet per minute. They're usually English. The forest guys, they use English. They don't use metric. And fire intensity, which is British thermal units per foot squared minute. And these were derived and integrated into a series of mathematical functions relating to such characteristics as moisture and mineral damping coefficients, slope factor, and wind coefficients, and all centered on the fuel. Okay. And there's his basic equation there. R is the rate of spread of the flaming front. IR is the reaction intensity, and it's a whole other series of functions defined as fire intensity. That, I think that's epsilon, I think that's what it is, a proportion of the reaction intensity that heats adjacent fuel particles to ignition. This is what I was talking about. That's why it's such a powerful factor. That heating front that's in front of the fire, that up to 1,000 degrees that can be in front of the fire front is very important. Okay, and then there's phi W. Actually, that W should be littler, but you get it. Dimensionless multiplier accounting for the effect of wind in increasing the proportion of heat that reaches adjacent fuels. Okay, and then there's phi S. It's another dimensionless multiplier, and it deals with slope rather than wind. So these two are kind of very similar, and you notice that they occupy similar places in the equation. That right there is the oven dry fuel per cubic foot, so you're taking into account volume. And another dimensionless number, that's a big one right there, accounting for the proportion of a fuel particle that is heated to ignition temperature at the time flaming combustion starts. And there's a caveat here which I find interesting. That's near unity for fine fuels, but it asymptotically decreases towards zero as the fuel size increases. So you're dealing with almost a surface roughness. You know, a fuel can be a log, okay? So that's a large size bit of fuel. But at the other end of the spectrum, the fine fuels are your particles when, you know, maybe underbrush has been dried for so long it starts to disintegrate and almost turn into a powder. That's your finer fuel. And then QIG is the heat of pre-ignition. And once again, that can be part of the fire front.
Because most of the fuel they're talking about is sitting on the ground, it's not the trees.
It can be the trees. It can be the trees. But often what happens is you get an overaccumulation of this brush, okay, and it sort of adds to the volume. And this is volumetric dependent, and that's what starts it. And then once you get that enormous amount of heat, and once that fire gets going, that's when you get the conditions where you get updrafts, and you get all of these conditions, which adds to the weather, the fire weather of this whole thing.
Yeah, that's where particle size evidently comes in, because fire weather is going to create a strong updraft to bring winds in from the side, like in front of the fire, that can bring in dry leaves, broken dry leaves, and of course those fine particles are virtually explosive.
Yeah, and they're so easily to get a wind to carry a 10-mile-an-hour wind. You get disintegrated leaf litter, just carries it everywhere. And once it's started sparking, it's going to catch tinder on fire. You know, that's why these things are so dangerous. There's Albini's nomogram. Albini was a brilliant mathematician. He's got pages of derivations and integrals that went into this kind of thing. I'm not going to go into that here, but needless to say, he took Rothermel's equation and his findings and refined them. And in around 1976, he came up with a nomogram. Now, a nomogram is actually used for a lot of other things, apparently. It's another type of model that is used to graphically depict complex mathematical relationships, and those are complex, relating to natural phenomena quickly and accurately. So you get Albini in here, and this is something he did by hand. He did this himself, and he gave this to the people that were fighting the hell-roaring and Shoshone fires, which I believe were going on in 76 or 77. He gave this to them, and they were able to see where they were. You have these series of curves of predicted models here that you can pinpoint where, and there's the behavior of the hell-roaring fire right there. It has a certain rate of spread, certain unit energy, mass joules per meter square, and then flame length. How long? What's the length of these flames? How high are they reaching? Are they reaching up to the canopy? There's the power of the fire, just the sheer power. And he graphed it all together in a lot of complex equations. And he gave it, literally, this is site-specific. This was for this fire, and he gave it to the people who were fighting the fire. Okay, models are continuously refined for specific use. Models aren't perfect. I read a paper written by some researchers in Greece that found that Rothermel's equations didn't quite work for them. Different conditions. Greece is a bunch of limestone that's been carved up. You know, there's not this dense underbrush like there is out west. It's a completely different area, so it didn't work for them. That's the way it is. It's natural science. It's never perfect. Science itself is based on a rigorous system of critical review, so it's part of it. Okay, one of the ways you input information into a model, like Rothermel's model, is you use remote sensing. Nowadays, you can find where a forest fire is using satellite technology. Today, wildfire management is a problem on a global scale. Satellite remote sensing of fires continues to approach higher levels of accuracy and resolution on a global scale. We're about to look into that. Despite this level of visibility, it's uncertain whether variability in land cover type, surface temperature, and fire regimes will permit the use of measured global temperature and reflectance threshold, meaning there's an area of uncertainty. You know, because you're trying to see an infrared signal that might not be a fire. It might be something else. So you have to correlate it with ground fact, ground truth, as usual. Trace gases and particulate species monitoring are of prime importance on a global scale. You can get a spectrographic analysis for maybe something like MODIS of what kind of gases you have. I mean, you can see a fire and its smoke because you can detect the amount of carbon monoxide and carbon dioxide that's in the air around it. And particulate species refers to particles in the air. It also can refer to aerosol-like particles that are thrown up by fires and a lot of other natural phenomena. Due to advanced fire monitoring sensors such as MODIS, reliable information, we can get pretty good information. Once again, you need ground truth. You have people on the ground that are confirming this. Okay, and the caveat is it's got to be coupled with data gathering, and the Forest Service does this. Okay, now this isn't really fire from space, okay? This is a colored and sort of time-dependent depiction of where fires occurred within, I think it's within a month. I mean, it doesn't look like that. This is like if you're looking at a picture of the Eagle Nebula in outer space. Well, they've colorized it. Well, the people that do remote sensing with MODIS colorize things too. You do that all the time. But this gives you an idea of how widespread. People clear cut, especially in the equatorial regions, through the Amazon. Of course, we're having a problem with people getting rid of forests in the Amazon. People are clear cutting using, it's over on the other side of the globe, but if South America was here, you'd see a lot of red on it too. People are clear cutting using fire. People clear cut the Congo with fire. There's something going on here. It's either natural or clear cutting. People clear cut in India. Clear cutting is a widespread practice. It's done everywhere. And it's not clear cutting, it's burning to make way. They also clear cut, and they do both. This Farsight is a model, it's one of the models. There's another type called Behave. Farsight's the one that's used mostly by the U.S. Forest Service. And it's a finite element model, not a finite difference model. It uses polygons over aerial space. It's called Fire Area Simulator. It's fire behavior and development, and it's developed finite element model used by several agencies, including the USDA Forest Service. It utilizes Huygens' principle of wave propagation, actually. They sort of added that into it, which is interesting. The fire fronts are seen as the front of a wave ellipse in this model. So they're modeling it as a wave ellipse. And if you think about it, there's convection going on there that makes sense. It makes use of digital elevation models, which is odd because those guys in Greece said the elevation was not working at all. Okay, Like I said, they're not perfect. GIS is used for slope, aspect, and elevation themes. So you can use, you get your signal, infrared signal, and then you can use the actual, what MODIS does, sort of visually imaging and altitude imaging where this fire is, and you can start putting your inputs in that way. You get a long, you get a long list of data in your computer, and you start inputting it into the model. Data sources must be entered manually, and these include existing vegetation maps. So they're probably taking USGS, 7.5 minute maps and putting it in there. In fact, that's what they're doing. Use satellite imaging analysis along with the ground truth data. Again, you clarify it on the ground before you send some guy out there to take a look, some guy or gal out there to take a look. Aerial photography and a lot of what's done is people will fly planes over these areas, and then they can gather data this way. In fact, most maps that you have that you can get at like a map library, like the one on the UGA campus, are based on flights rather than satellite. The historical data, there's tons of them. Farsight supports data in ASCII format, and you can plug it into 2D ArcView if you're using ArcView. So, what you see this little circle here? Okay, that's where the fire started. Okay, this is a model built from Farsight, right here, and it's gonna propagate this way. And if this was working, you'd see it sort of like. It's hard to explain. Oh, like a stain of water. Like if you take a white tablecloth and you blot it with some wine or something, and it starts spreading outwards. That's not exactly, but that's a lot like what this looks like. And it shows you over time, because you get this clock here, once you've modeled it, what the probability of this fire, what probability it has of being here in, let's say, 20 minutes versus here. Well, here you see a lot of, it looks like rock. You could have a body of water somewhere. It's not going to cross it that readily, but you have some vegetation and you have certain conditions, say it's real dry, and look at all that forest. Well, it's going to be way up here versus here in maybe 30 minutes. That's how Farsight works. And I've seen it work, and it seems to make sense. And this is all done, before any fire occurs, or maybe after a fire occurs, to see if your ground truth matches the modeling data. You compare the two. Okay, MODIS is one of the satellites where we get information for fire modeling, provided by NASA, and two satellites, the Terra and the Aqua satellites. MODIS scans the entire planet every 1 to 2 days in 36 discrete spectral bands. And MODIS is used for a lot of applications, not just fire, fire prevention. There's a whole host of GIS applications that it's used for. MODIS data is highly useful for inputs into a variety of geographic, climatological, hydrological, and geological models, including FPM, fire prevention models, and fire prevention models, another type of model. There's more than just Farsight. There's Behave, FPM, Farsight, and a bunch of others. So it seems that MODIS does a lot of sort of earth science-based imaging, geological, hydrological, climatological, and geographic. Okay, there's a MODIS image, and there's the slices it takes, and it covers the planet, and I don't know why it's variable, but it covers the planet in 1 to 2 days, both satellites. And there's the URL. Active fire map. This you can get online with this URL, which we're about to get to, and see where fires are occurring. This is what MODIS is telling us right now, where these fires are occurring. Okay? It's kind of similar to the one we saw. There's one here, Ranger Complex in Arizona. Okay. Got one in Florida. Yeah. That's fine. No. Let's look at it. Okay. Cause lightning, you see, they've got people, you're imaging it, and then you've got people on the ground going out to take a look at it. You've got somebody that reported it as lightning. Okay? The fuels, here's the fuel. The fuel's predetermined. We've already determined what the fuel is. One short grass, timber litter. Very interesting. Okay. Can we look at another one? Okay. Let's see what's close to home.
One in Florida,
Yeah, yeah.
Kentucky.
Let's see the one we can go to right now. Yeah, Kentucky. Okay. Cause human. Oh my gosh. Okay. Somebody caused that. You got medium fuel. I suppose medium, since fuel is size dependent, so medium-sized fuel, whatever the metric for that is, probably small timber, wood, something like that. And let's take a look at the one in Florida.
All right.
Oh, cool. Okay. It's going to be interesting. Marion County, they don't know the cause. They haven't figured it out.
It's not John Bronson.
Yeah, no, he's the guy on the ground for us. Litter and understory. Understory is anything below the lower canopy in the forest. Medium.
Yeah, Pine Castle bombing range, I wonder if the Air Force did that to themselves.
Oh, maybe so. Maybe so. And then the causes, it's the Air Force. They don't want to tell us. Yeah, they're keeping it hush-hush, you know. Yeah.
Classified.
Cool. Okay, see, you can find out so much, you know. Modus is telling us a lot, and you just get on a website. Can we?
When you see fuel here, it says litter and understory. How finely do they model that? Like different kinds of litter, oak versus sweet gum versus pine litter? I mean, these have very different
Yeah,
combustion.
they do. You have to consider the type of litter, the type of plant. Wood is cellulose material, has all sorts of different properties, different fibers, you know. There are different water contents too,
And
moisture.
Pine litter, dry pine needles have the remains of resins in them that will burn. I mean, it's almost a hydrocarbon.
Yeah.
Burn very readily.
Exactly.
When we looked at Arizona, it was talking about grass. I mean, how finely do they model the type of grass that's burning?
Apparently, it's really important. So I would
think so.
I would think there's a roughness coefficient.
Worldwide, we've got 20,000 species of grasses, and they
Yeah.
probably all have different combustion rates.
They're probably looking at the actual size, the physical size, or they're looking at volumetric content because you get a volume of this stuff, and I would almost imagine that there's some sort of surface roughness coefficient for this kind of stuff because
And then,
it's really important.
I mean, in prairie systems, you don't have just pure grasses, but you have grasses intermixed with shrubs. At lower sites, you would have more moisture than you would have over ridge tops.
Yeah,
I
exactly.
imagine it gets extremely complex.
Very complicated, and that's why Rothermel created a fairly simple model, and somebody like Albini came along and added so many more parameters and state variables too. Because in modeling, you have your parameters and you have your state variables. Your parameters basically stay the same. State variable is just what it says, it's a variable. It's dependent on other conditions. It's functional, you know. So, yeah. Can we look at that again? I wanna
Okay, sure.
just see where there are more fires. Okay, there's none in California. Let's see the one in Louisiana. That's kind of interesting. You don't think about that with Louisiana, but Louisiana actually is a very well-forested state. Lightning, okay. Longleaf, loblolly. We got a lot of longleaf and shortleaf pine in South Georgia. Blue stem, hardwood timber. Yapon. Yapon is a type of plant that grows, I believe, in the barrier islands. You got some in like Sapelo Island and Jekyll Island. And so, okay, lightning caused this. So they got accurate. Team leader, there you go. You know? So, I mean, this makes fire prevention, actually our fire prevention system in this country is very efficient. And once again, because you need controlled burning, it's too efficient. You need to actually get out and burn that sort of that understory, that undergrowth, because it'll build up and cause out of control fires.
But if only 7% of the fires are caused by lightning, which is the only natural source,
People.
I mean, it would seem like there are enough fires that we cause.
Yeah.
Is that not true?
Well, and then there's that huge portion of the pie that's arson, you know. That's semi-creepy. I mean, you don't think that people are out there purposefully burning natural lands, you know, but they are.
Well,
Maybe
in
by
Colorado,
proxy.
was it last month or before, there was a big fire near Boulder. Wasn't that set by, was somebody in the fire department that was burning debris at his house?
Oh, okay.
And his house, among many others, burned down.
So, human folly, you know? Yeah, so put out your forest, put out your forest fire, put out your campfire, you know? I mean, it's old Smokey the Bear type, you know, message. Right, the prescribed fires are, you know, the idea is you control them, and they're not, I believe they're not done, if there's a lot of wind, they don't do these things. I mean, they don't want them to get out of control.
I've seen places where they've been done, and yeah, usually they make sure it's a dewy, foggy morning
Yeah.
before they set the fire, so it's not going
Yeah.
to get out of control.
I've seen them too. I've seen them. They're kind of like where you go down, you drive down through South Georgia, and you see these places where the fire just stops. They just stopped it, you know, and they meant to put that fire there. And it's if you end up going to school at Warnell, you know, they'll probably have a class, you know, how to do prescribed fires. You get to go out in the woods. I have a paper that I did for this too, and so a lot of this stuff. And there's Merle Dixon's, you know, a guide for prescribed fire in southern forest. Dale Wade. Just it was recently. It's been added to. That, you know, they've come up with new techniques. But it was originally published in 1989. You can get it online, U.S. Forest Service. And there's Rothermel's original paper. He did it at the that place in I think in Missoula, Montana, is where he was stationed. So okay, there's the citations, and then we'll the last slide. Any questions?
You said this MODIS satellite's an infrared imager, huh?
It's got a lot of instruments on it.
You said a 32 band, sounds like it's got like 32 different infrared filters or something like that.
Mhm. It does infrared. I think it does ultraviolet. It does a lot. I mean, the USGS, Forest Service, a lot of people. You know, I guess for satellites you reserve time or you reserve space in satellites. You have to you know, sort of fill out a form to NASA, I guess, and get space and time. And you know, what these people do. I guess there's people that are getting grants. What's that?
Submit a proposal for.
Yeah. And then once you get the proposal, you have time. You have space on that satellite, and it's sort of a subscriber service as far as I understand. I think it is. It's a subscriber service, so you can get information off of them. So it's a good thing. It's a good thing because you have the eye in the sky up there that can see broad areas that we can't see on the ground. A forester, forest ranger can only see line of sight. And once you get that broad area, then you get a human to go down there and get ground truth, take data. You can take actual temperature data, specific temperature data. You infer it up there when you see an infrared signal. You kind of go, okay, it's got to be in this temperature range. And you don't even know if it's a forest fire or whatever it is. And you get somebody on the ground, take specific data, and then you correlate the two. You've got to compare your model to ground truth. That's what you have to do in general. Okay.
Well, Steve,
Your
Go
your
ahead.
model, or models you've talked about all apply to wildlands, national parks, forests, grazing lands.
Mm-hmm.
Is it applicable too to urban areas?
Mm.
I've been thinking about this since you first gave us a definition at the beginning.
Mhm.
You know, these are out-of-control fires that can jump roadways, they can jump rivers. It sounds like the Chicago fire in 1871.
Yeah.
Burned, what, 4 square miles? And
I would hope that
jumped the Chicago River at least twice.
I haven't researched urban fires. They're, of course, probably of greater concern to all of us. I would imagine there are really pretty technically minded people at work. That's maybe something we can look up.
You know, I know a lot of urban fires are pretty well controlled, but then,
Yeah.
was it in Detroit a couple of weeks ago? There was whole blocks that burned.
Mm-hmm.
Of course,
Yeah.
a lot of those houses were vacant
Yeah,
because Detroit has
Detroit.
such high unemployment, people
Yeah.
moved out.
It's like Baltimore. You go through Baltimore and there's just row after row, of
Right.
just nobody there.
Sad to see.
Yeah. I would imagine that, somebody's modeling for urban, because you can model microclimate in urban. I mean, from having taken geography courses and climate courses, there's a thing called microclimate. So this is we're in a microclimate right now. You go downtown Atlanta, you're in a climate. Urban areas impact anything outside of them. We have an urban heat island. Heat's sent up. It's the summer. Here comes some rain, picks up the heat, updrafts, and you get a thunderstorm over in Gwinnett County. Right. Yeah, see, it's getting dry now. We're almost in a drought.
My question is about, how would you rate the chances, I mean, we have, the fire weather that we have going on right now. We had months of droughts, maybe just, a little bit of rain every 3 weeks.
Well, it would be your relative humidity, and sort of relative humidity patterns. For how many days on end do we have relative humidities down in the 30% tile? And the more days like that, I'm certain there's somebody at the U.S. Forest Service who's looking at it, tabulating the data and making charts and going, wow, we're getting into a drought again. Because it rained recently, but it just didn't rain enough. Out where I live, just a little sort of spurt, and then dry the rest of the time. I mean, and the gardens are, they're collapsing.
They're parking up for a day and
Yeah, they're like,
wilted.
come on, give us more. Yeah, exactly. Yeah, that's important.
You showed a map of fire hazard for the whole U.S. or something.
That was for 1 month. They make those continuously.
What's that based on? I mean,
Reports.
they-
The reports, like,
But I mean, that's the hazard, right?
they take it from...
Measurements of the water content of fuel or something like that?
No, just where they report a fire. And they do that for the whole month, and then you go, okay, there's a likelihood of the next month. You use that map for the month the next month, the month you're in now, from the previous month, because conditions don't abruptly change from month to month. Nature doesn't have a calendar and goes, okay, it's January, we got to stop this. So you use it to predict. It's another prediction tool. You use the previous month's data for this coming month. That's your likelihood. Depending on what kind of weather you might be getting into, and things change constantly. This is why it's good to have satellites up there, because you can monitor these changes, minute by minute.
Steve,
Oh, yeah. Yes.
The Weather Channel app on my phone. And
Oh,
I'm
cool.
getting fire weather watches for about the past 2 weeks.
Really? Here?
Yep.
See,
North
We're-
Central Georgia.
we're in trouble.
Yeah.
Yeah. I don't know if we're in a drought yet, again, but it doesn't rain much soon. We're gonna be there again. I mean, we just got out of an enormous drought, caused a lot of damage. I mean, Lake Lanier just turned into a puddle. What's going to happen again? I don't know. So it's good. Apps are good. Okay, is there any more questions?
No,
Okay,
I
well,
guess-
thank you for coming.